Good morning. So this is where we've so far. And this is everything up to here you need to memorize. We will give you potential energy terms for various potential energies. So the energy principle is very simple. It says that if once you choose a system, the final energy of the system is going to be the same as the initial energy of the system plus whatever energy inputs there are from the surroundings, and this can be either positive or negative. And so far the only kind of input we've talked about from the surroundings is actually mechanical work. And work is the sum of Fx, the force exerted in the x direction times the displacement in the x direction plus Fy delta y plus Fz delta z. We can write this, of course, as F dot delta r, where that's the vector dot product. And for a system that has more than one object in it, for a single particle, there's only two kinds of energy you can have: rest energy and kinetic energy, which is associated with motion. For a multi-particle system, there's the rest energy and the kinetic energy of each particle, plus interaction terms. So for every pair of particles, there's going to be a potential energy term that relates to the energy between the two particles. So for a system of three objects, like the Earth and the spacecraft, there really are three potential energy terms. There's the potential energy of the Earth interacting with the spacecraft, the potential energy of the Moon interacting with the spacecraft, and then the potential energy of the Earth interacting with the Moon. Now, since that isn't going to change as the spacecraft, very noticeably, as the spacecraft wanders around in that system, we can safely leave it out, but it's safer. You can also just put it in and then note that it's not changing. And the potential energy change is equal to the work done by forces internal to the system. And we use that to derive an expression for the potential energy of gravitationally interacting objects. And today we're going to go a little further. So today what we're going to do is very briefly talk about what this the thing that was incorrectly on the board at the beginning of class, the change of potential energy near the Earth's surface, why we can use mg delta y for that. And then we're going to talk about electric potential energy, explore graphs of energy, and talk a little bit about some general properties of potential energy, like path independence and choosing initial and final states when you're solving a problem. So we have that near the Earth's surface, the change in gravitational potential energy was in mg delta y, and we got that from saying, well, the work done by internally was mg delta y, but it actually is related to this expression So the change of potential energy is minus g m1 m2 over our final minus g m1 m2 over our initial. And so near the Earth's surface, this would just be a minus g mass of the Earth, mass of our object, over the radius of the Earth plus delta y minus if the object went from somewhere on the Earth to somewhere above the Earth, right? And so actually to calculate this, we'd have to do some algebras. So we'd have to find the least common denominator by multiplying this side by RE over RE, that side by RE plus delta y over RE plus delta y. And if we do all that, we get to an expression that's minus g mass of the Earth, mass of our system, divided by times delta y divided by and radius of the Earth squared plus radius of the Earth delta y, and that's just algebra. You can work it out for yourself. Well, the radius of the Earth is really big, so the radius of the Earth squared is even bigger. So we can say that this term is 0, and that gives us a minus g mass of the Earth, mass of the system. And am I right about that minus sign? This was a minus delta y. That's what. Mass of the Earth, mass of the object, over the radius of the Earth squared, delta y. So this comes out to this minus times that minus, which comes from multiplying this side by that over that. So that comes out to a positive number. And we saw before that this thing is equal to little g. So really this mg delta y, so we get this approximate value near the Earth's surface. And it's just algebra. But it's useful because if we were calculating having to use the radius of the Earth every time we did calculations of things happening near the Earth's surface, that would be awkward, and we'd be subtracting very small numbers from large numbers, and that would not give us good results. So so the real gravitational energy of a system, and why is it delta U here that we're talking about? Well, the real gravitational energy of the system near the Earth's surface is a minus g mass of the Earth, mass of the object over radius of the Earth plus an mgy, and so the potential energy, the total potential energy, really actually is negative. But since this piece isn't going to change when we're talking about changes near the Earth's surface, we just don't worry about it. Okay, so electric potential energy. So I remind you that when we talked about electric forces, we had unlike the gravitational case where massive objects just plain attract each other all the time, the electric case was more complicated because particles that had the same sign of charge, like two negative charges or two positive charges, would actually repel each other, and only charged particles of opposite sign, like proton and electron, would attract each other. And that makes the potential energy a little more interesting. So we have positive charges and negative charges repelling each other, and a positive charge and a negative charge attracting each other. So it seems like the potential energy of the system ought to be, could be either positive or negative. And it turns out that that's the case. Remember that we had the electric force between two particles had this odd constant 1 over 4 pi epsilon sub 0. The charge of one particle, the charge of another particle over, I'll just write r squared here, r hat, right? And the sign of the component of the force, the direction of the force, depended both on r hat and on the signs of both charges. Well, the electric potential energy works the same way, and we calculate it the same way by taking remembering that in one dimension u of x is the x component of the force was the negative gradient, the negative spatial derivative. That's not a very good u, is it? Of the potential energy, and if we take an antiderivative, it turns out that the electric potential energy is equal to 1 over 4 pi epsilon 0 q1 q2 over r, where r is the distance between them. Remember, the potential energy isn't a vector, so it just depends on the separation of two objects, not on the direction. And so Q1 and Q2 have the same sign. Is this quantity going to be positive or negative? Yeah, it's positive, isn't it? If they have opposite signs, then it's going to be negative. So we can get electric potential energy terms that are positive corresponding to repulsive interactions, and negative corresponding to attractive interactions. So let's see here. Let's look at some examples. All right. So we know what the graph of gravitational potential energy versus separation looks like, right? In fact, we're very familiar with this after having added graphs to the Ranger 7 model. So which graph correctly shows the dependence of electric potential energy on separation for a proton and an electron? So think about it for a minute. Talk to the person next to you. So what do you think? What's the answer? Okay, I see. Well, okay, so most of you are saying 1, some are saying 2, a few are saying I have no idea. So that's okay, let's talk about it. So how do we figure this out? Well, one way is just to look at the equation. Okay, so this is just a constant. And these are signed numbers, and that's just distance, right? So just like the gravitational potential energy, we know that when r gets really, really big, the potential energy has to approach 0. So we can definitely rule out 3 because the potential energy doesn't go to 0 as the particles get farther apart. It gets bigger, not smaller. So that's we can rule out 4 for the same reason. So as the separation between the particles gets large, the potential energy is not going to 0. So 3 and 4 are not options, right? Now, so it's a 1 over r curve then, and the sign. So the question is, what's the sign? Well, if we have a proton and an electron, this product is negative. So basically, this looks just like the gravitational potential energy for 2 objects attracting each other. We get this minus 1 over r. And as they get extremely close, it gets very, very negative. So, thinking about graphs. Questions about that? Okay, so what would it look like for 2 protons? Okay, so what's the answer? 2 is correct. So for 2 protons, this quantity becomes positive. We have a positive 1 over r. As r gets small, it gets really big. So So it looks like for a repulsive interaction, the potential energy term is actually a positive. And as these objects get closer together, potential energy increases. And as they get farther apart, potential energy decreases. And 2 protons coming together, shot toward each other with some speed, as they come closer, since they're repelling each other, they're actually going to slow down. So their kinetic energy decreases, and that means the potential energy of the system has to increase. So it sort of all hangs together here. Okay, so we can use this to solve problems. So suppose the problem we had was we have 2 electrons that are far apart and they're heading straight toward each other. with some initial speed v. And the question is, how close do they get before they come to a stop? So what's the distance of closest approach? So this is the energy principle for this system. There's only one potential. If we take both electrons as the system, then there's one potential energy term due to the interaction of the two electrons. We've left out the MC squared terms. We could put them in, but we know that they're not going to, the electrons aren't going to react with each other, and so their identity isn't going to change. So we can ignore change of identity here. So that's our energy equation, E final equals E initial plus inputs from the surroundings. So which of these terms are not 0 in this equation? Yeah, consider them to be really far apart initially, okay? Okay, so what's the answer? Yeah, very good. It's 6. That's right. So we didn't talk about anything in the surroundings that was going to do any work on them, so we can assume that that's 0. Initially, they're very far apart, so this potential energy term is approximately 0. But they do have a lot of kinetic energy because they're moving toward each other. In the end, they come to a stop. So therefore, their final kinetic energies are 0. And we're left with U final is K1 initial, 2 initial. Now, the problem said find the distance between them when they come to a stop. What is that hiding in this equation? Is it in the kinetic energy? Is there a distance in kinetic energy? No. So it's got to be here. And in fact, if we write it out, we get a 1 over 4 pi epsilon 0. We have, what are these, 2 electrons? A minus E times a minus E over R final, and that, in fact. Yes, Robert? Good point.
Excellent question.
Other questions? Okay, so which of these graphs shows the potential energy and the kinetic energy and the sum of potential and kinetic energy for this system of the 2 electrons that are coming toward each other? And well, yes, I mean until they.
So is it stop?
Yeah.
And they're both constants. Yeah, so they should go to right? Yeah. Well, it's getting okay,
So what do you think? What's the answer? Okay, we're very divided. I see 4, 3, and 2. So let's think about how we think about this problem. So this is energy. This is separation. Now, is this a repulsive interaction or an attractive interaction? Repulsive. So the electric potential energy is going to be positive or negative? Positive. Okay? We know it has to go to 0 at... So what you do is you sort of pick locations where you know something and put a point and then figure out what happens to the graph. So we know it has to go to 0 at big distance. We know it has to be positive. We know it has to get really big as they get close together. So that has to be the electric potential energy. Now, what do we know about kinetic energy? We know that when they're far apart, is their kinetic energy 0? No, it's positive, isn't it? So out here, kinetic energy has to be positive, and it decreases as they come together, and at some point it's got to go to 0 because they stop. And so in fact the kinetic energy for this particular system pretty much has to look like that. That makes sense? Okay, so how do we draw the sum of kinetic and potential energy for this system? Well, yeah, we just actually have to look at values here and say, well, if U goes to 0, then the sum is going to be K, basically. And since there's no external work done on the system, what has to be true about the sum of kinetic and potential energy? It's constant. So we know that K plus U has got to look like that. So the key is to pick things you know, whether it's the shape of a potential energy curve or values of something at some point, put them on the graph, and then start from there. So this is some other system. For which of these, so assume that the graphs of kinetic energy and potential energy are correct for this system. graph is the sum of kinetic and potential energy drawn correctly. Pretend it says 1, 2, 3. Okay, that's right. It has to be A, doesn't it? Because we have potential energy going to 0 here, but the kinetic energy is non-zero, and it's going to go up, and therefore K plus U has to be that value. So there's not that much to it. You just have to think about what you know. Okay, so given what you did last week in lab, if we have a comet and a star, or think spacecraft and a planet or something like that, in which case is the comet gonna escape from the star and never return? Okay, so what's the answer? Okay, so I see 1s and 4s. And 1 is definitely correct, because it's clear from the graph that when the comet gets to a large distance from the star, it's still got a lot of kinetic energy. It keeps going. So it definitely has enough energy to keep going and not come back. So that's correct. What about this one? That is exactly right. This is having the right amount of kinetic energy to escape, but coming to rest when it's infinitely far away. So if K plus U is exactly equal to 0, then it slows down, progressively getting farther and farther and farther and farther away. And when it gets infinitely far away, it's at rest, but it's gotten infinitely far away, so it's escaped, hasn't it? So that is also a correct answer. This here, it just can't get that far away, can it? And that's called, so if kinetic energy is, if the K plus U is less than 0, we say this is a bound system. Okay, it has to stay together. You would have to put in energy to separate the two objects. Now there's kind of an interesting thing about this bound system graph. So we have potential and attractive potential energy here. We have K plus U, and the kinetic energy, it's almost to zero there. So what happens when they get further away than that? Well, the answer is they can't. It's basically a forbidden region. So this particular system just can't get there. And we would need to put more energy in the system to get it to be able to separate. Questions about that? Yes?
And it's going to fall back.
Oh, yes. It'll, of course, go back the other way. Which, yes, Charles?
That essentially means that like the maximum distance for a bounded orbit is set by that potential energy.
The maximum distance, well, the maximum distance for a bounded orbit is set by the sum of K plus U, right? And so I think you saw that last week. So to get a circular orbit, you started with one speed. To get an elliptical orbit, you had to make the spacecraft go faster, right? And to make it escape, you had to make it go even faster. So that meant you were putting different amounts of, the potential energy remained, the curve, the function for potential energy remained the same, but you were putting different amounts of energy into the system to produce orbits that went farther and farther and farther and farther away until it finally managed to escape. So let's see if we can use these ideas to solve a problem. And the problem is this. How much energy do we have to put in to ionize a hydrogen atom? So well, okay, basically this is an escape problem, isn't it? Because we've got, in a simple model of the hydrogen atom, here's the proton, here's an electron moving around in some sort of pattern, but we'll say it's orbiting at this radius. So we use the Bohr model of the hydrogen atom, which isn't awful. It actually gives the right answers. It's a pretty useful model. So the first thing to do, we want to do is we want to think about, we're going to apply the energy principle, right? So the first thing we always do is we write down the energy principle. E final is E initial plus work. And how is work done? Well, we might shoot a high energy particle at the hydrogen atom and it would knock the electron out. Okay? So how much energy does that require? So let's think about what we want to choose, first of all, as our system, and second, what we want to choose as the initial and final states. So choice of system, both particles. And initial and final states. Well, initially, the electron is basically one atomic radius away from the proton. Now this is an estimate, right? And the final state is when we've got, so this is initial. The final state is when we've got the proton and the electron infinitely far apart with the electron with zero kinetic energy, because that's the minimum amount of energy for it to escape, right? Okay, so let's think about what terms have to go into this equation. So what's one thing I should put here? K initial of the electron plus K initial of the proton plus U initial plus our energy input. And over here we've got the same terms except final, right? K final of the proton, U final. Now we don't really know the initial kinetic energy of the electron. So let's just assume for now, this is an estimate anyway, assume for now that it's about 0. Is the initial potential energy 0? No. Is it positive or negative? Negative. And what's 0 over here? Okay, they're very far apart. What's the kinetic energy of when they're far apart? Yeah. This problem just got a lot simpler, didn't it? So all we have to do is calculate that initial potential energy, and we know how much energy we have to put in. So is minus U initial is minus 1 over 4 pi epsilon 0. The charge of the electron is going to be minus 1.6 times 10 to the minus 19 coulombs. Charge of the proton is plus 1.6 times 10 to the minus 19 coulombs. The radius of an atom is roughly 10 to the minus 10th meters. And this has the value of 9 times 10 to the 9th Newton meters squared per coulomb squared. And that comes out, when we do this calculation, to 2.3 times 10 to the negative 18 joules. And that's kind of a small number, so we probably want to convert to electron volts. So we divide by 1.6 times 10 to the minus 19th joules per electron volts, and we get something on the order of 14 electron volts. Now the actual number is on the order of 13.6. that's not a bad estimate. Yeah.
Why do we call the initial kinetic energy of the electron zero?
Because we don't know what it is, and that's one of the flaws in our estimate. So the question is, why do we call the initial kinetic energy of the electron zero? It's probably not, but we don't know what it is. So we're going to say if it were zero, then it would require this much energy to ionize it. And that's one of the flaws in our estimate, because we don't actually know the initial kinetic energy of the electron. And it's one of the reasons we're off a little bit. Yes?
Is that the only flaw, or is there any other reasons why our estimate is wrong?
Is that the only flaw? Well, this is a very simple model of the atom. And so the electron isn't actually spending all its time at exactly that radius. So that's another issue. But notice that it's actually, we're really in the right ballpark here with a very simple calculation. So, not so bad. So, let's see, where are we? Okay, we have time. So let's think for a minute, and we'll do more with this in recitation. So questions about this? So let's put up the electric potential energy up here. Actually, let's think for a minute about general properties of potential energy and what we know about potential energy. So the first thing we know is that it's a property of interaction between two particles. A pair of particles within a system. We know the potential energy must go to zero as R goes to infinity, because if we get an electron and a proton really far away from each other at rest, the energy of the system is absolutely mc squared for the proton plus mc squared for the electron. So U has to be 0. We know that U depends on separation. And that has some interesting consequences. It leads to path independence of change in potential energy. And what does that mean? Well, first of all, if we have some object here, suppose there's another object interacting with it in the system, and it goes from here to here. And we want to calculate the change, so this is our initial location, and this is our final location. Does it matter how it gets there? So it could do that, or it could do that. So whatever happens in between, there's no history in here. Whatever happens in between is irrelevant. If we're just considering this initial state and that final state, we know the potential energy for each of these configurations, and so the change of potential energy for the system from that initial state to that final state has got to be the same. What does that tell us about a round trip change? So if here's our planet, here's our spacecraft, it starts here and does something weird and comes back here. What's the change of potential energy of the system? That's 0, isn't it? So delta U round trip is going to be 0. And one final thing we've done is U can be positive or negative depending on when the interaction between these two objects is repulsive or attractive. Questions? All right, let's think about sketching out a solution to a problem. And the problem is actually a fusion reaction. There's more than one kind. So suppose what we want to do is shoot an alpha particle, which is a helium nucleus with 2 protons and 2 neutrons, but no electrons, at a carbon atom with sufficient energy that there's actually a nuclear reaction that happens, and what we make is an oxygen atom plus a photon. So the question is, how much kinetic energy does this alpha particle need to overcome the repulsion with the carbon nucleus and actually react? Now, what is repulsion with the carbon nucleus? Well, this thing is moving fast enough that it actually just kind of blows the electrons away. Okay, it just kind of scatters them. We can see this, even though it's positive. Here we go. So what we're going to do here in this program is just shoot an alpha particle past a stationary electron and see what happens to the electron. So here's the alpha particle, it's positive. Here's our electron that's sitting here, it's negative. Here's the velocity of the alpha particle. The electron is definitely attracted to the alpha particle, but it gains enough energy that it just gets scattered away. Okay? So the alpha particle is just going to sort of blow past all the electrons and then interact with the strong force with the nucleus of the carbon atom. So our question is, how much kinetic energy do we need to make this happen? So we want to choose the system as the alpha particle and the carbon atom. So all particles, basically. What do we want to choose as the initial and final states? Think about this for just a second. Yeah.
What do you mean by states? Like the particles themselves, or like?
When we talk about initial and final state, we're talking about the configuration of the objects in the system. About ionizing the hydrogen atom, we picked as our initial state the electron 1 atomic radius away from the proton, and our final state was part. So state means a configuration of the objects. Yes.
So would the state for this system be the velocity or kinetic energy of the?
Well, the state is a configuration. It's not a value of a quantity. So the state is the particles in some configuration with an amount of energy. But basically the state is defined by the configuration. And so I drew this here with these both at rest because we were talking about an escape problem basically. But so what's the initial state? Yeah, the alpha particle and the carbon atom far away from each other. So that's sort of clear. So here's the alpha particle. Here's the carbon nucleus. The alpha particle is heading toward the carbon with some speed and therefore some kinetic energy. Now there's a couple of possible final states we could consider. So one is clearly, so that's an initial state. One final state would be the oxygen and the photon with some, actually since their initial momentum has to add up to that, maybe they're both going that way. But is that the only possible final state for our analysis? What we want to find out is how much energy we've got to get to make this reaction happen. What does that mean in sort of our, translated into our physics terms? Yeah, it means how much energy do they need to get close enough that they touch? because the strong force is basically a contact force, and therefore these two things have to actually come in contact. So another choice of final state would be the alpha particle touching the carbon nucleus. And once that happens, then the reaction can occur, right? And that seems like a better choice because if we know what this distance is, well, let's just write down the equation. We have so for our choice of initial and final states, the initial state no work done on the system here, so we have the kinetic energy of the alpha particle plus the carbon is at rest plus m alpha c squared carbon c squared plus u initial. And over here the reaction hasn't happened yet, so we have the final kinetic energy of the alpha particle plus the final kinetic energy of the carbon plus the same rest energies because they haven't changed. So is anything else, so what else is zero here? Well, we're assuming the alpha particle and the carbon nucleus are far apart to start with, right? So what's the potential energy term? Zero. What's zero here? We just want them to barely get close enough to touch so the kinetic energy can be zero. Final potential energy is not zero. Now what didn't change here? Rest energies, okay, so yes, I know. Quiz. So these didn't change, but now we have actually a fairly simple equation. The final electric potential energy is equal to the initial kinetic energy of the alpha particle, right? And if we know the radius of the carbon atom, then we can actually calculate this potential energy and get the energy we need to put in to make this reaction happen. Yes?
Question. Would the radius be like half the bond length of the three carbon atoms?
What's the distance? Yeah, we're going to, I mean, again, we would estimate it. So the alpha particle is smaller than the carbon atom because it's got, but we could estimate this as 2 times 10 to the minus 10th meters, or we could be more exact and try to, what?
Nuclei.
Oops, right, nuclei, sorry. So there was a radius of a nucleus, guys. It's about 10 to the minus 15th meters. So we can be more exact if we want to, but so basically even rather complicated problems are very simple, but the analysis, the upfront analysis of choosing the initial states and choosing the final states is actually the sort of physics piece. Then the rest is just kind of turn the crank.